guys, once again welcome back. Okay, so in this part we will be discussing, or we are moving one step towards the bar magnet, and whatever you have done in the Coulomb's law of electrostatics, we are going to see that how it is applicable for, or what is the Coulomb's law of magnetism. So this is what we are going to see. So for that, let us proceed. Now guys, dipole moment of a bar magnet and Coulomb's law in magnetism. Now let's proceed. So dipole moment of a bar magnet and Coulomb's law in magnetism. First review the bar magnet. Okay, so we have seen that this is the bar magnet and these are the pole. This is north pole and this is the south pole. We have already looked this, and this is the magnetic moment of the bar magnet, or it is, so this is the magnetic moment of the bar magnet, and I have already told you earlier that we will going to define this. So we are defining this thing. So this is magnetic length, and this is magnetic length is the length between the two poles, that is north pole and the south pole. Okay, next we have the geographic length. It is the length between the two ends of the magnet. Now we have already seen that what is the ratio of the magnetic length upon geographic length. It is 0.84, and we can see from the figure that this is less than magnetic length is less than the geographic length. Now let's proceed. Now if we talk about the magnetic dipole and the dipole moment, so let us define what is a magnetic dipole. So a pair of magnetic pole of equal and opposite strength separated by a finite distance is called the magnetic dipole. So it's a thing that we have to understand, that the pair of magnetic poles, that means again the same thing, no isolated poles. Okay, now what is a dipole moment? Now let us define the dipole moment. It is the magnitude of the dipole moment is the product of the pole strength m, and we denote the pole strength, that is the for a particular bar magnet, pole strength is the strength of the, that means how much is the strength of pole, what is the capability of that pole to attract the magnets, or to attract or repel or attract the other magnet or other objects. So this is called the pole strength, and this is the pole strength, and we denote this pole strength by m. And the separation between the two poles, that is what we call the magnetic length, and this length is 2L, and this is between the two poles, and we call this as the magnetic length. So it is the product of these two. So therefore let's write this as, so this is actually the m into 2L. Capital M is equals to m into 2L. This is what exactly is the thing, and where this denotes the direction. Now we will come to the direction. This factor denotes the L cap, that is the direction along L cap. Okay, now the SI unit of pole strength is ampere meter. Now if the SI unit of the pole strength is ampere per meter, then what we are doing, we are multiplying the pole strength with the length, that is m into L. So m into 2L, 2 does not have any unit, so therefore this is ampere meter, so this is ampere meter into meter, so therefore m, the SI unit of magnetic dipole moment, will comes out to be ampere meter square. Same thing. Now if we talk about the direction of the dipole moment is from the south pole to the north pole along the axis of the magnet. Okay, what is the axis of magnet? We have already discussed this thing, that the axis of the magnet is the line joining the two poles. This is the axis of the magnet. This is axis, and this is the south pole, and this is the north pole, and the direction of the magnetic moment is this m vector from south to north. Okay, let's proceed. Now what is the Coulomb's law in magnetism? Now Coulomb's law in magnetism, the force of attraction or repulsion between two magnetic poles is directly proportional to the product of their pole strength. That means, what does it mean? If you place two magnets together, something like this, So these two magnets will attract or repel each other depending upon the configuration or depending upon the orientation of the magnets. So it is something like this. These are the two poles of pole strength M1 and M2, and there will so these two strength will going to feel some attraction or repulsion, or else we can say that these will going to feel some interaction. So what do we say? That this force of attraction or repulsion between two magnetic poles is directly proportional to the product of their pole strength and inversely proportional to the square of the distance between them. This is the r, and this is r, distance between them. This r is distance between them, the two pole strength. That means numerically what we can say, force is directly proportional to m1 into m2, force is inversely proportional to r square. So therefore what we can write? So we can write this as F is equals to K m1 m2 divided by r square, where K will be the proportionality constant. Okay. Or else what we can write this as? We can write this as F is equals to mu naught m1 m2 4 pi divided by r square. Okay, now let's proceed towards the dipole moment of a bar magnet in magnetism, where K is equals to mu naught by 4 pi is a constant, and mu naught is equals to 4 pi into 10 to the power minus 7. 4 pi into 10 to the power minus 7 Tesla meter ampere inverse. Okay, in vector form, this force can be written as F vector is equals to mu naught m1 m2 r cap divided by 4 pi r square. That means this shows the direction of the force. So it will be repulsion or attraction depending. So whether it is attraction or whether it is repulsion, so this force will be along the r cap. Okay, let's proceed. So this can be written as F vector is equals to mu naught by 4 pi m1 m2 r vector divided by r cube. So why it is written as r vector divided by r cube? Because r cap can be written as r vector divided by r vector magnitude. So therefore if we substitute this value of r cap in this equation, we'll going to get the same thing. Okay, now let's proceed towards the examples. In examples, a bar magnet of pole strength m and a magnetic moment m is divided into two equal pieces by cutting along its length. That means if I have this as my bar magnet, so I have cut it into two pieces, something like this, along the magnetic axis. This is pole strength, let's say south pole. This is let's say north pole. So for a particular bar magnet, if this is the one bar magnet, so pole strength will be same, it will not be different. So therefore this is m, this is m. So if we cut it along the magnetic axis, this is axis, so if we cut it along the axis, so what we are going to get? So pole strength will going to get divided into two parts, that is pole strength. Now new pole strength m dash will become m by 2, and this is length, this is length L, the distance between the two poles. So what do we write? What do we know? So we know that capital M is equals to m into L. So if we talk about so initially it was m is equals to m into L. Now if we talk about the new new dipole moment, let me write it as m dash. It will be again from south to north direction wise. So magnitude will be m dash into L dash, that is the new length. Now it has cut, or it has cut in along the axis, so L dash will become L. So therefore this can be written as m dash into L, and we know that m dash is equals to m by 2. So therefore this will comes out to be m by 2 into L. Initially it was m, initially this was m into L. Now it is m into L divided by 2. So therefore m dash is equals to m by 2. So what we can say, m dash is equals to m by 2, capital M dash is equals to m by 2. So what do we say from this? What we concluded, that the pole strength has got divided by 2, or pole strength has got half, or the dipole moment also has got half. So therefore let's look at the options. So according to the option A, m is half but m remains same. No, option is wrong. M is half, both are half. Okay, therefore option B is true. Now let's proceed towards the next example. Two identical bar magnets are placed perpendicular to each other with the north pole of one touching the south pole of other. Now this is the figure. Now if the magnetic moment of each magnet is capital M, okay, so we have learned that the direction of the magnetic moment is from south to north, so therefore it is the magnetic moment for this rod will be M in this direction, and magnetic moment for this second rod is in this direction from south to north. So both will be M because length are same and the pole strength are also same. It is this we can see from the figure. The magnetic moment of each magnet is capital M, then the magnetic moment of the combination is. Now if we make the figure, this figure looks as if the magnetic moment is in this direction M vector, and in this direction. So we have to add these two vectors by the vector law of addition. So we can add it with the triangle law of addition. So therefore this will comes out to be this is AOB. So if we need to find out AB vector by the triangular law, it comes out to be OA vector plus BO vector. So therefore this will comes out to be M vector, since they are asking about the magnetic moment of the combination. So magnetic moment of the combination, I'm finding out the magnitude part. So magnitude part will comes out to be, so since both the magnet, the angle between both the magnet is 90 degrees, so therefore what will comes out to be m1 square plus m2 square, or m square plus m square. So therefore this will comes out to be resultant m net will comes out to be root 2m. This will be the resultant final answer. Now this figure is something like this. This is the bar magnet. Now we can see it in some different way. We can see this question in some different way. So this was the south pole. Okay, this was the south pole, this is the north pole, this is the north pole of this magnet, and this is the south pole. Now what we can say, that this is the configuration. Now if we look at this thing, we can say that this has got neutralized, because south pole has got neutralized with the north pole. Or what do we left with? This is the magnetic strength, pole strength, this is the pole strength. So what do we say, that these pole strength are left, and this can be treated as a new bar magnet having length. If this is L, this is L, this can be written as root 2L. So this length will be root 2L. So therefore what we are going to get, M will comes out to be, since pole strength are same, so M into L, that is in this case it is root 2L. So therefore M net will comes out to be M into L into root 2, or this M into L is the magnetic moment of the initially placed bar magnet. So this is M into root 2, or M net is equals to root 2M. So if we look at from this thing, answer will comes out to be same. If you look at by the first method, the answer will comes out to be same. Means both the method, you apply both the method or else any method, the answer will comes out to be same.
So guys, we have seen that what is a dipole moment of a bar magnet and how the Coulomb's law, that those you have studied in the electrostatics, how these are applicable in the magnetism. We have already seen this thing in this part. Now we have the next part in which we are moving us one step ahead towards the magnetism, in which we will going to see that what are the certain terms that we will going to use. So these are the what are the certain important terms we will going to see. So for that part, stay tuned.